Hi there, it's Miss Heaton signing in to talk about intermolecular forces, or IMFs. We're going to be kind of switching gears. So far in this unit, we've been talking about bonds, so covalent or ionic bonds within a molecule. These are intramolecular forces. The options for this are covalent or ionic. Intra means within. So in these molecules down here, the bonds we've been talking about are the bonds that stick atoms together. But in this lesson, we're going to be talking about the forces that cause one atom or molecule to be attracted to another. So we're going to talk about the forces between two different molecules. These are intermolecular forces. And we're going to call these IMFs for short. Why do we care about this? Well, this is actually the driving force behind why water is a liquid and so many other covalent substances aren't. So that's kind of where we're going with this. So you see water here, and you see three different water molecules. And because these molecules are attracted to each other, they're going to stay close together in the liquid form rather than becoming gases. So if those forces weren't there, water would not be here, and thus we would not be here. So what you want to do is make a chart for what we're going to talk about today. We're going to talk about 4 different kinds of forces. And what you need to know about each of them is where they're found, like what kind of compound are they found in, and then maybe like a description of how strong they are and what exactly causes them. So the first force are London Dispersion Forces, or LDFs for short. We got several acronyms going on. These are actually found in everything, but they really only are important in non-polar molecules, and I think I'll write that in. I think it will show up again later. These are most important in non-polar molecules. These are the weakest force, so they may be overridden by stronger forces. So this is how an LDF, or London Dispersion Force, happens. So let's say we've got 2 atoms. Maybe it's xenon, or something with lots of electrons. It's got 80 electrons, or I don't have a periodic table in front of me. However many electrons it's got, they're around the nucleus, spread out. Now, at any given time, those electrons are allowed to move within the orbitals, and it's possible that a bunch of them could congregate on one side of the atom. And if you have more electrons on one side than the other, what happens? Well, that side gets to be a little bit negative, and the other side gets to be a little bit positive. And that creates a dipole. So we end up with a kind of negative and a kind of positive side. This is that partial charge that we saw in the polar bear and penguins reading. And when that happens, that's going to cause a nearby atom to have a similar dipole, because if all the electrons over here, they're like, hey, we're having a party, and the atom nearby says, oh, wait a second, similar charges repel, so my electrons are going to move to the other side as well. And then that causes the 2 atoms to be attracted to each other, because one side is negative, one side's a little bit positive, therefore they're attracted. How does this affect boiling points, taking a liquid and turning it into a gas? Well, look at it. If you look on the periodic table, the bigger or heavier the molecule is, the stronger the London Dispersion Forces, right? Because neon's at the top, followed by argon, krypton, xenon. So as you're going down the periodic table, the boiling point gets higher and higher and higher. So the stronger the forces, the higher the boiling point. Now, this applies to molecules that are bigger, but also to different forces that are stronger. So we're going to come back to this idea at the end of our lesson. Force number 2 are dipole-dipole forces. These occur between polar molecules. So polar molecules also have LDFs, but since polar molecules also have these dipole forces, and the dipole forces are stronger, these are going to be more important in polar molecules. So here we see a molecule, maybe like water or sulfur dioxide, that has a partially positive end at one end and a partially negative end at the other. And just like we saw in our last case, we know that negative and positive attract, so there's going to be a little attraction between these 2 polar molecules. This is going to be a little bit stronger because it's more permanent, whereas in our London Dispersion Forces, those electrons are going to move back to where they came from eventually. Here, we always have a positive and negative end due to having a polar molecule with different electronegativities. Okay, force 3 are hydrogen bonding forces. Now, these are not bonds. You've heard about these before in biology. You hopefully have already heard this. They are not bonds. Remember, bonds refer to things within a molecule. We're talking about forces, so maybe we could call these hydrogen bonding forces, so that you remember they are between different molecules. Now, these are a special kind of dipole-dipole force. They're basically just like dipole-dipole forces, but they're between molecules that have even more polar bonds. So they're like super dipole-dipole forces. And they only occur when you have a molecule that somewhere in there has an H directly connected to an F, an H directly connected to an O, or an H directly connected to an N. So here's an example. We have water, right? Water has an O and an H bond. Actually has two of them. Since it has those bonds are pretty darn polar. So this end ends up being pretty strongly negative, and this end ends up being pretty strongly positive. That will attract a different molecule of water. And here is our hydrogen bonding force. This dotted line is our hydrogen bond. It is between two different water molecules, each of which have a pretty darn polar bond in them. So these are going to be a little bit stronger than a regular dipole force because, like I said, they're a little bit more polar. And this is, again, why water stays as a liquid. Because it has such a strong bond, it has a very high boiling point. If we were just looking at elements in the same period as oxygen, it goes oxygen, then sulfur, then selenium, then tellurium. If you go down that group on the periodic table, you would actually predict maybe that the boiling point of water would be about -100. That's pretty cold, right? Because water freezes at 0 degrees Celsius. Earth never gets down to -100 degrees Celsius. And so at room temperature, water would definitely be a gas. So there would be no water left. So we are very grateful that we have hydrogen bonding happening because that allows us to exist based on water. Okay, our fourth and final force are ion-ion forces. These are, as you might have guessed, found between ionic compounds. It's the strongest intermolecular force because ions have full positive and full negative charges, not partially positive and partially negative. So what happens is that the positive ion, like sodium, in one compound, if we had sodium chloride, the sodium's positive, the chlorine's negative. We've talked about this being a compound of NaCl, but it's not actually. That's why compound is in quotes. It actually is a formula unit because that sodium chloride is going to find another sodium chloride and line up with it so that the opposites are not next to each other. Or sorry, the opposites are next to each other. The same charges are not next to each other. And then that sodium is going to attract a chlorine in a different compound. And that's going to happen over and over and over again, creating this whole network of forces that hold those ionic compounds together. So these are the strongest force. So if you've got one of these, it's definitely going to have the highest boiling point. Okay, so to summarize, the stronger the intermolecular forces, the more energy it's going to take to break that force. Therefore, they're going to have a higher boiling point. It's going to take more energy, more heat to break those forces and turn it into a gas. The force with the lowest boiling point would be LDFs because they are the weakest. The highest boiling point would be ion-ion forces. Now, it's possible that you would have to compare two different compounds that have the same kind of force. If that happens, the tiebreaker is the molar mass because the heavier the molecule is, the more electrons and protons and neutrons it's going to have. Therefore, the more likely it is to have stronger forces occurring, even within the same kind of force. So if they have the same IMF, the one that has a heavier mass will have the higher boiling point. By the way, let's pause for a second and think about this. How do the forces we're talking about here compare to bonds? What do you think is stronger? Is it a covalent bond or an intermolecular force? I'd actually like you to think about that, and we will talk about that tomorrow in class. Okay, let's try some practice here. Remember, the stronger the force, the higher the boiling point. But if there's a tie, if they have the same kind of force, then it's the heavier mass. Heavier, heavier mass. That's our tiebreaker. Okay, so in our first compounds here, we have BaO. Look at your periodic table. Barium is a metal, therefore BaO is an ionic compound. So it would have ion-ion forces. Okay, how about HF? H is a nonmetal, as is F. Therefore, this is going to be some sort of covalent compound. And if we were to draw the Lewis structure, it would look something like this. Oh, you know what? I see that we have a hydrogen bonded to an F. That means that this is going to have hydrogen bonding forces. This HF might be attracted to another HF with a hydrogen bonding force. Okay, so let's see. We'll compare our two kinds of forces here and figure out which one's going to have the higher boiling point. We've got ion-ion versus hydrogen bonding. Ion-ion is stronger, therefore our BaO will have a higher boiling point because it has a stronger force. Okay, practice problem number 2. We've got CH4 and C2H8. These are both covalent compounds, so we can rule out ion-ion. So it's a good idea to draw those Lewis structures. You got CH4, looks something like this. Well, we know that CH bonds are nonpolar. So even without drawing the Lewis structure, we would know that this is a nonpolar molecule. Therefore, this has LDF forces. And C2H8 is going to have kind of a similar structure. Carbons with hydrogens all the way around. Again, it's going to be nonpolar, so that's LDF forces. Uh-oh, we got the same kind of force. What do we look at to figure out which one boils at a higher point? Well, that's where we look at our tiebreaker, the heavier mass. Now, even without adding this, you could probably figure it out. There's more carbons and hydrogens in this one, so if you add up their molar masses, it's definitely going to be more than the CH4. So this one's going to have our higher boiling point because it is heavier. Okay, folks, here's the one that you get to try on your own. Compare Cl2 and CO2. Bring that to class and we will discuss it tomorrow. Hey, one last thing here that I forgot to mention. LDF forces can actually also apply to atoms. So if you just had like xenon, it would apply to xenon. It would apply to a nonpolar compound like C2H6. Or sorry, C2H8, I guess both of those would apply. So LDF applies to anything, but especially to atoms and nonpolar molecules. Okay, folks, I believe that is it for tonight. Remember, Cl2 versus CO2, bring that to class tomorrow, and may the force be with you. Ms. Heaton, signing out.